thing that we're going to look at is the chi-squared test for independence, and this test is applied when you have two categorical variables, for example, gender and eye colour, and this comes from a single population, and the reason we use this test is to determine whether or not there's a significant association between those two particular variables. So what's the basis for using the chi-squared test? Well, the sampling method's usually simple random sampling. The variables that are under study are categorical, and the sample data is displayed in a contingency table, and for exam purposes the expected frequency count for each of the cells, it will be greater than or equal to 5. You need to do some tricks otherwise, and I think that could be part of the IA. But the whole idea about statistical testing and hypothesis testing is, first of all, to state the hypotheses, to formulate your plan, to analyse the sample data, and then to interpret the results. And so usually what we start off with is a null hypothesis, which is stating that whatever variable A, it has no effect on the level of variable B. In other words, variable A and variable B are independent. And then you've got the alternative or null hypothesis, which is usually stated that variable A and variable B are not independent, or in other words, dependent. So with regards to the types of contingency or size of contingency tables you get in the exam, Virginia informs me that there's a maximum of 4 rows or 4 columns, that the degrees of freedom is always greater than 1, critical values are always given, and we use these traditional significance levels either at the 1% level, the 5% level, and the 10% level. And so the idea is to, well, what we used to do in the old days before calculators was to calculate a test statistic. Now what we'll do is we'll calculate a p-value, and the p-value is always the probability of observing a sample statistic as extreme as the test statistic. And you determine whether to accept or not accept H0, or the null hypothesis, depends upon the p-value. So typically you compare the p-value to the significance level, and you reject or don't accept the null hypothesis when the p-value is less than the significance level. So we go to the next page. In general, these contingency tables have a dimension R by C, where R is the row and C is the column. Now, it's my understanding that any expected frequencies that need to be calculated, or in terms of being asked to calculate an expected frequency in an exam question, you're expected to do that by hand. And the formula for this is the product of the row total and the column total, and then divided by the grand total. So we'll see an example of that in a moment. The other important thing, of course, is the number of degrees of freedom of the chi-squared test statistic, and it's given by the product of the number of rows, take away 1, multiplied by the number of columns, take away 1. You could go into a discussion of why that's the case, and it makes a lot of sense if you set up or show tables that give the marginal totals, and you can say, well, if we work out 3 of those, then we don't have to work out the 4th one, and that's where this idea of 4 minus 1 or 3 minus 1 actually comes from. So the other thing is that the chi-squared test of independence in such a size contingency table is based on this test statistic, which is U. U is equal to, or how do we calculate it? It's equal to the sum of the differences of the observed and expected values squared divided by the expected values. And what happens is, through some fancy pants, some statistics that you probably won't mention to the students, is that test statistic actually follows quite closely a distribution called the chi-squared distribution, with a particular number of degrees of freedom which is dictated by the product of R-1 and C-1. And that's true. That's the case if H0 is true, provided that the expected frequencies are greater than 5 for most categories. So here is an example. Now, it's pretty likely that in the exam those marginal totals here and here, in other words, row totals and column totals, won't be published, but anyway, that's okay. So here we have a situation where a sample of 300 individuals were asked to select a preferred colour from blue, red, green and yellow with the following results. So your categorical variables are gender, male or female, and then you've got your preferred colours, blue, red, green and yellow. And the idea is to test to see whether there's any gender difference in colour preference. And so what we do is we first of all state our null and alternative hypotheses. So H0 is that there's no association independent, and the alternative hypothesis is that they are not independent. And so this particular page illustrates expected frequencies, and it illustrates how 3 of them were calculated. And for exam purposes, it's important that students are able to calculate an expected frequency for 1 or 2 entries, I suppose, of such a table. So for example, if we look at blue and male, it's equal to, the expected frequency is equal to the row total, which is 100, multiplied by the column total, which is 120, and then divide by the total number, which is 300, and that gives you an expected value of 40, and then they've been calculated as shown and specified in brackets. So you end up with a set of observations and a set of observed frequencies and a set of expected frequencies. And then what you do is you, or what's the calculator, which we'll show you in a moment, what it does is it calculates that the sum of O minus E all squared divided by E, and gives us a test statistic which we can compare against the critical test statistic. So we go to the next page. I think it's a really good idea actually to show students what's going on underneath the hood of the calculator. There's the calculation of the test statistic. Now we'll jump ahead a little bit and then we'll move back and show you how to use the handheld. So the degrees of freedom is 3. It's the product of 4 minus 1 and 2 minus 1. And so therefore you use the chi-squared distribution where the degrees of freedom is equal to 3. Now what we used to do in the old days was we could use the chi-squared CDF, which is the cumulative density function, and put in our test statistic, comma, a really, really big value, because this distribution's got an extraordinary long tail, and comma, the degrees of freedom. That actually represents our p-value, and as the p-value is less than, let's say, 0.05, then we reject the H0 and conclude that there's an association between colour preference and gender, i.e. there is a gender difference in colour preference. And you can then, not for the purposes of tonight, you can go and see where these biggest differences actually occur. So how do we operationalise this on the calculator? Well, what you might want to do is on a calculator page, you might want to assign the observations and call it a matrix, call it OBS, and then we go to the open book button, which is the catalogue button, and then we want to set up the dimensions. I think were 4 rows, and we wanted 2 columns, so we press OK. So that's our observed frequency matrix template. And so now if we add some values, so for the males are column 1, so that's 30, 30, and then 50 and 10. And then the females were the second column, and they were 70, and then 60, and then 20, and then 30, and then press enter. And so what we've got now is we've got our observed matrix defined. And now if we go into menu, and then statistics, and then stat tests, and then chi-squared two-way test, and then type in OBS, which is our observed matrix, and press OK. What we'll see here is we'll see that's our test statistic, 38.39. On a previous page it said 38.40. There's our p-value, an extremely small p-value. The degrees of freedom is 3, and we can get the students, we require the students to interpret these results and then state a conclusion. Now, after completing the test, if you press var, then you can call up the p-value individually. For example, there you can call up the degrees of freedom. You can also call up the expected frequency matrix. And so that's the expected frequency matrix, where column 1 is the males, column 2 is the females, and you can compare it back to here. Those values in the brackets correspond to these values here. So you can do this test in the calculator application. You can do it in the notes application. You can also do it in the lists and spreadsheet.